Welcome back to our lecture series on GPU architectures and programming. So, if you remember in the previous lecture, we have been talking about optimizing the GEM computations. So, we discussed one optimization which was thread coarsening, application of thread coarsening over a tiled matrix multiply. Now, let us start with the next optimization. So, if you remember our previous optimization, we increased the amount of work per thread and that was in the column dimension of the output, right. Well, why do we say it is the column dimension? Because when we are giving the examples, it is essentially we are talking in the rows, but since it is basically in the column measure format. So, of course, it will be the whatever is the row measure format of the mathematical matrix is actually the column dimensions there, right. Now, we can just apply the same optimization trick for the other dimension, right. But how do you really do it? Well, the way you can do it is by using wider data types. Now, what is a wider data type? We will soon see, but let us understand how this is really going to help. First of all, for this optimization, we will not carry over the previous optimization here, although we understand that using both optimizations together can help. So, now let us consider that we are just considering how a wider load instruction can really help me, right. So, this is actually done by using vector data types instead of loops over the work per thread variable that we discussed earlier, right. Now, in NVIDIA GPUs, we do not have support for vector operations like vector multiply or vector add like vector operations in CPUs, and of course, we do not need them because we are having multiple scalar units which work using the idea of warps in all that, but so we do not have vector operations, but there is something called wide load and store instructions both for the off chip as well as the shared local memory. So, what does that mean? Well, I am not going to have multiple additions or multiplication operations happening on vector data, but I can have vector kind of wide loads, right. I can load multiple data together using a suitable vector data type. Let us see how that really works. So, when I am really using a wide data type, one example would be this float 8. So, essentially if I declare a float 8 kind of variable, that means let us say I am now making this A sub and B sub arrays which are in my shared memory. I am declaring them as of type float 8, and that would mean each element in that array can accumulate 8 consecuting floating point data, fine. So, that also means that well I do not need that much width of A sub that was there earlier, right. So, I decrease the column dimension here for A sub by Ts by width, right. This is a Ts is tile size, right. So, that is how now my A sub and B subs will get reduced with respect to columns, but on the contrary what is happening, each of the elements are getting wide by 8, right. Each entry in the matrices will now be having 8 consecuting floating point data. Again, why are we really trying to do it? Well, we are trying to increase the total amount of data that is there, I mean while it gets loaded both from the global memory. So, from global memory when I am using one load instruction, I am making it explicit that you load these many together, right, and put it in a wide variable. And similarly, consider this as a shared memory and you are trying to load it into the GPU register for doing some operation, that will also be a wide load from the shared memory. So, now of course, the usefulness of the instructions can be exploited only if we can change our program suitably. So, what will be the changes? Now, let us understand the implication here. So, what we are really looking at now is something like this, that you have so let me first draw one tile. So, in this tile we are saying that well, so this is one tile inside that entire C matrix, something like that, right. Inside that tile I am saying that well, the thread should compute let us say a wide number of, let us say some multiple entries together, right. I am again I will say I am drawing now in the column dimension, because now they are going to be, these are the things that will be accessed in parallel, right. So, now if you see that how the wide loads are going to happen here. So, again we have the outer loop tiles to number of tiles, which remains tiles iterating from 0 to number of tiles, which remains same, and here I have the loading part to the shared memory, right. If you remember in the previous quotient version we introduced a loop here, well that is not going to be there, because now I am not applying thread quotienting, I am just applying wide loads, right. So, now when I am defining this operation, that well from the global A and B arrays you load values to A sub and B sub. So, this since the data type here is this floatate, so I will have the wide vector loads operating, right. So, with each load I will get multiple, let us say since it is floatate. So, I will get 8 consecutive float values getting loaded into the tiles, right. But then there is a problem, right, let us understand. So, I mean if the mathematical arrangement of the data was like this, and like we discussed that well you will have one row here to traverse and you have multiple columns to traverse, right. So, you multiply like this is in the mathematical domain. But now, when you are trying to work it out for these many data points here, what do you really need in the input tiles that are A sub and B sub? So, if you have to get this done, then you need data here like this and you need values like this, right. This is the requirement, you want to work on them, right, and they are all located, right. These values, since it is a column measure format, they are all located in one entry of the matrix, right. These values again they are located in one entry of the matrix. These values they are again located in one entry of the matrix, but you do not really want to multiply this entry with this entry, right, because since this, you really want to multiply these entries with these entries to get this value by using normal mathematical matrix multiplication. I hope this is clear. Let me draw this thing again in a better way. So, we will just say I want to compute more elements in the matrix row. So, I will employ a wider load instruction. This will help me to compute multiple values together. If I employ the wider load instruction, then what I get here in the A sub and B sub. So, this is B sub and this is A sub. So, then I have data here like this, and due to collaboration I am drawing in terms of 4 instead of 8, just because of course we need to get the meaning correct, and the wider load instructions here are giving me values like this, right. The point I am trying to make here is, well, to compute this we understand that we have to go like this, but how is the data there in the variable? That is the problem. The data is there, these consecutive data points are there in one location of A sub, the next set of values are there in the next location of A sub, right. That would mean I have to now look inside the value and segregate individual parts from the value and then use them to do component wise multiplication and compute these values, right. Let us figure out what does that really mean. So, now after the loading is done, which is very simple, let us go to the compute loop and see how things are going to change. So, of course, this is the outer loop for the computation, this is the outer loop for the computation, right, but the issue is with the inner loop, because as I am saying that for computing each of these values I need access to consecutive values in A sub, because each of the values here they are of vector type and I need to look into each of the components. So, what do we do? Well, we take B sub value in some vector B which is fine because I need these values which are anyway together. But for A sub, I have to have a loop which will run through the entire width, which is 8 in our implementation, consider it 4, right. In each iteration I take one element of A sub. In the first iteration I take one element of A sub. What I am really supposed to do? I am supposed to look into each of these components individually, multiply them by each of these components and store them as partial sums here. In the next iteration of this inner loop, I am going to take the next A sub value, which is again accessible as one of these, right. But then I have to look inside it into its components and I have to multiply these components again with the B sub values. I hope this is clear. What is the problem? Because I have them in these columns, right. Since they are in columns, but actually I need to compute like the rows. So, I have to look inside the components. That is what is done by the switch case. So, here as I progress through this inner loop with respect to w equal to 0 through width, what really am I doing? In each iteration of this loop, I pick up one of these A sub values and then I sample out, well, for each thread I am trying to sample out which component of this vector I would be interested in, right, because A sub I know that I know that I have picked it up and I have stored it in vk, right, but I have to realize now that for the other vector, this one, which are the components with which I am going to multiply them, right, because as we know that for vk, this first component, the first component of vk needs to be multiplied with the first component of the vec b. Of course, let me first define. So, vec b is storing this, right, and vec a is storing this value right now. In the next iteration, vec a is going to store the next value like that, right. Also, we need to figure out a way to access the components. Now, for float data types, the way is that you just do a normal structure like computation, like so. For this vector vec a, you do a dot S0 that gives you the first component, dot S1 is going to give you the second component, so on and so forth. So, what do I really need to do? So, you take vec a and you need to multiply vec a's S0, I am speaking for w equal to the 0 case, right. So, what do you need to do? You need to take vec a's S0 component and multiply it with vec b's S0 component, right. So, for w equal to 0, I need vec b's S0 component. So, that is why I pick up this, right, and here what am I doing? I am multiplying vec a's S0 component with this, and that gives me the partial sum for this. But parallelly I have other things also, right. For for this right now I have with me in val b, I have vector b's S0 component. Well, do I need it for some other computation? Of course, I would need it here for S0, but in future when I pick up the next vec a, I would again need it, right. So, let this so here what is happening for when I am accumulating for the S0 component, this is what I am doing, but what about the other components? So, as you can see right now, for all the other components also, let us say this component, I would need vec a's component S2. So, let us say the third component, that is S2, I would need vec a's S2 component to get multiplied with S0, right, which is already in val b. So, that is what takes place here, right, and similarly for all the components. I hope we are making some sense here. So, essentially what am I really doing? By using this switch case, we are picking out this value, the first value, and then I am in by all these accumulation statements, we are multiplying this S0 component of the vec b with all the different components of vec a, right. and that is what I require. I require all these values to get multiplied with this as a partial sum for here, right, which we again I have to update later on, and this continues, right, with the loop making progress. Now I will take the next value of vk, right, and for each component of vk I will then again I have to sample out what to do for which component of vec b to pick, which will be the next component, and I will now use this component for all the other ones, right. So again, as you can see, there is lot of saving happening, like for with one load for this vec b, whatever component I am getting, I am choosing the appropriate component and I am doing the multiplication of that component with everything else for the first component of the vector a, right, and that way this computes, right. So just to summarize, for this multiple values, for each of them I am making a vector load like this and I am multiplying these vectors different components with the components that are here, right. I am just choosing which component to multiply, because if we can understand, for this computing this value I need this one to get multiplied with this, for computing the next value I need the next one, that is vk dot s1 to get multiplied with the same value. For the next one again I need the vk dot s2 to get multiplied with the same value. That is why I am choosing this value here using the switch case, and I am using that as val b in all the accumulations. Again, as I progress, I will choose one component here, right. I will choose the second component, right, for vec b this value. By the way, it is important to note that vec b is loaded once and that is getting used entirely in this loop, right. Vec b is not changing. In one iteration of the loop, as long as I am inside this inner loop, right, I am inside this inner loop, I have this vec b, right, and here inside this inner loop I have this vec b. So once I load it, for each of the components of them I am just figuring out which component to multiply with the different components of vk, and I am just using it. So I load vec b once, I load vk multiple times, the number of times that is required to fully do the compute of the final entries, and in each case I select the suitable component from vec b and do a multiplication with all the components of vk, and that is how it progresses. So as you can see that this is just a different idea with respect to thread core chaining. What we are doing is, we are for per thread we are doing wider loads, so that I get more amount of data per load, and then that gives me a problem, like the data is all in columns. To use them in a suitable way, I make use of this intelligent loop structure here. Now coming to the next optimization, which is rectangular tiles. So what is this? So if we see in our previous examples, we just use tiles of size, I mean we just use, I mean earlier for also for matrix multiplication typically we use tiles of size 32 cross 32. Now that requires how much memory? Well, two of the shared memories, each of size 32 cross 32, right. So 32 cross 32 times 2 multiplied by 4 bytes because it is float, so 8 KB per work group, right, or let us say per block, I mean like that I have this per work group 8 KB, right. So that is not much. Why? Because even if we consider as Kepler's old GPU like Tesla K40, it has 48 KB of shared memory. So I have more shared memory there, right. So what I can do is, I can create bigger tiles, right. So there is a small mistake here. So this is called creation of rectangular tiles, right, and also there is something important that I can do, that since I am multiplying A and B together, and as you can see from B I am doing an access. So for A, the data, since it is a column measure representation, so that means for A the columns are there in the memory, right, but for B, I mean for B is basically I need the data in the other way around, right. So as we know that when you are multiplying matrices and loading data, for one I will get this memory coalescing effect for loads, for the other I will not get it, right. But a good way to optimize that is that, well, we transpose the other matrix. So in this case I can just transpose B, right. So because if you see that for B I have the access which is not memory friendly, so I will just transpose B, because we have already figured out earlier in our discussions with respect to matrix transpose computation that it is really possible to do very efficient transpose computation, where the amount of the amount of time required for doing a transpose is not too high with respect to a normal memory copy, right. So assume that we first do a transpose, so that the matrix B is available in the global memory in a transposed way. Well, what does that help in? Well, now when I have B in transposed way, now when I am bringing data, I get the good effect of memory coalescing happening for both matrix A and B, right. So now let us just go through some basic definitions. Right. What we do is, let us say TSM define the tile size in dimension m, TSN for dimension n, and the tile size in dimension k is 32. Okay. And also we will increase the work per thread. So, we will bring in the previous optimizations, right. So, we will bring in the work per thread corresponding optimization, let us say 8, and with this, what is the reduced tile size in the dimension? So, as you can see that since I have more work per thread, so the tile size in the dimension n would be, you just take the actual dimension divided by the work per thread, right. So, in general, what is the total number of loads per thread for a single tile? How many loads you really have to do in a single tile? Well, that would be, you multiply the tile size in dimension k multiplied by the tile size in dimension m, you divide it by the reduced tile size, right, for both the dimensions, right. Just like RTSN, I can have an RTSM, right. So, you have the original tile size in the dimensions, you just reduce it. I mean, you just divide it by the reduced tile size, because now you are going to do more activity per thread. So, that tells you what is the number of loads that you have to do for each thread. So, let us call it LPT loads per thread, right. Now, once we start using all this, again we will not try to discuss the entire thing in great detail, but we will just try to identify that how things are really going to help us. So, first thing, the first optimization here for rectangular tiles is that, well, we have taken B as a already transposed, right. So, that would give me some acceleration when I am loading data from the global memory for both A and B, right. But then there is a problem. When I am loading the data, if you look at the previous codes. So, let us look at the previous code of Courtsand version, which was optimization 2. So, this is how I was doing the load, right. So, from B I was transferring the data here in B, right, which in the shared memory representation of B, right. So, so that was all nice when from B I was loading. Well, the load was not coalesced, but the store in the shared memory was really happening in consecutive locations. So, that when I read the data, it is already in a good in a nice way, it is arranged properly, right. But now, when I am loading from B transpose, I will have a opposite effect here, right. When the data is getting stored in the shared memory, I actually lose the advantage which I gained for the shared load by doing the load of the transpose. Well, does that mean that I do not want to do a B transpose from B? No, I really want to do it. Why? Because global loads are expensive. I really want to minimize the time there. So, definitely I will do it, but what I will also do is when I store here in the shared memory, I will flip the indices. So, that is what we do. If you see here, I have row here in the second index, but for rectangular stores, we will actually load in the opposite way. Yeah. So, this was your original quotient code for optimization 2. As you can see, I have flipped the indices for B sub here. So, row comes first, right. So, that means, well, I am loading in a nice coalesced manner, but also to preserve the advantage of storage in the shared memory and not losing out on that, what I do is I flip indices here. Fine. I hope that clears this out. Apart from it, the rest of the things are fine. Only issue is you may just check that we have used a bit of OpenCL semantics here, like get group ID and all those, which of course, this is a CUDA code we are trying to see, and so that you may just replace it with a suitable CUDA formats here. Fine. So, once that is done, we have got an advantage that now my loads are optimized, and by flipping these parameters here, I have also kept the advantage of having consecutive data in shared memory in a proper way. And then, as you can see, you have a normal sync thread, and then a computation of the data just like previous things. But there will be one problem here, which you have to understand, that here again, when you are going to load the data from the shared memory, that is these operations, when you are going to load the data from the shared memory like this. So, this is where you are doing the accumulation, right. Now, just to remember that what really we did a coalesced load, we enabled coalesced load by doing a transpose previously, but then to get the advantage of having a nice situation, I mean nice consecutive operations in the shared memory, I have flipped the storage here, but that also creates a problem, because when after I flip the storage, what I get is the data gets stored in the shared memory like this. So, then that would mean that I will have lot of bank conflict when I am now loading the data from the shared memory to the accumulation loop. Again, this is a bit tricky, so let me just repeat. I just loaded I just made nice coalesced loads from the global memory, but since it is all transposed data, so when I am putting it in the shared memory, it is coming for the mathematical matrices columns, right. So, and that is not the exact order in which you will like to access them, right. So, in order to alleviate that problem with respect to access of the shared memory, you have switched columns here. Now, once you have switched columns here, the problem that comes with respect to the warps which are going to access this shared memory, just look at the way the warps are going to access the shared memory. So, here when you are accessing the shared memory B sub, you are moving by columns, right. You are operating on columns, because this is just for your alleviating your issue with the storage, but now when you are going to operate the data from the shared memory, you are accessing first by columns, and then your warp moves over to the next k, right. Now, this would give you a problem, because now you will have lot of bank conflicts. So, we will do a simple optimization that we have studied earlier, which was just putting in extra locations which are just padding locations, so that earlier without padding, that is having extra locations in your shared memory in your array in the shared memory, your data would have come in like this, but now your data would be coming in like this, because for this is the first data, right, and then after all the paddings, the next data point is here, next one is here, next one is here. So, these are the data points which the warp will actually access, right. I hope this is clear, but still I will just repeat. So, we have already understood why transpose is necessary. but as we understand the difficulty with transpose would be that when you are next, I mean of course, in the shared memory you are not having the regularity of the data that you were having earlier, because you have optimized the loads, but now your stores have actually disturbed the consecutive nature of the data. In order to preserve that, you have switched the row and column indices here, but then the problem due to this would be that when consecutive thread IDs in the warp will be accessing the shared memory, they would get their consecutive required data points in the same bank. For alleviating that, we use the padding trick that we learned earlier, which is just to add extra locations here, and all you do is you will just add extra locations, put in more than that is required, and that would actually again offset the locations here, so that when the warps are going to load the data, you avoid the bank conflicts. Fine. So, that is the good thing about rectangular tiles, and so helps you in optimizing global loads. And so the second important thing is you made the changes to optimize the shared stores, and then you padded the extra locations to avoid bank conflict. Now, why 2 locations? Why not 1 location? That is also an important thing, right? The reason is, in your shared memory now, for Kepler and other next generation architectures, the banks are 64-bit wide, right. So, that means you have 2 consecutive data points sitting in the same bank anyway, right. So, if your warp is accessing 2 consecutive data points, it is going to have a bank conflict. So, if you give a padding of 2, then you are forcing that, well, this is the memory locations I am showing, right. So, this is one bank and this is the next bank, right. So, in that way you are forcing that two threads in 2 consecutive threads in the warp access different banks, and there is no conflict, right. This is the important thing, that why the padding is by a factor of 2, because the warps are going to do 64-bit loads from the local memory, and the loads are 64-bit per thread, since the shared memory bank width is also 64-bit. Fine. So, with this we will end the current lecture, and then the next lecture we will look for some other optimizations. Thank you for your attention.